You are watching Chapter 4, A Model for the Cell, one of a series of videos on contractions of epithelial cell sheets. The purpose of this model is to provide a framework for discussion, interpretation of observations, and the planning of new experiments. A model is often known to be a simplification of the real world, but this may be an asset. Here we see cross-sections of two ampulla. At the top, the diameter is small. It is contracted. Cells are long in the radial direction, and cell-cell contact area is large. On the bottom, the diameter is large. It is relaxed. The cells are now stretched along the circumference, and cell-cell contact area is small. These are the major components in our cell model. At the bottom is the region of cell-cell contact. The magnitude or size of contact is measured by the number of molecules of cadherin that fasten the two cells together. The signal generated here is detected by a system of GTPase molecules. These process the signals and relay it to molecules that increase or decrease the length and number of actomyosin molecules. The model I will present here is an extension of this diagram, published in 2017 by Grissel. The black arrows indicate stimulation of one component by the other. The black line ending in a bar at rho indicates inhibition. The red inhibition line from the drug bibliostatin is not relevant to our model, but is included only because it was part of the original figure. This diagram presents important ideas, but is not sufficient to define a complete model. There are many possible combinations of pools and interactions that could be used to make models like these. A significant fraction are systems that oscillate within specific ranges of concentrations. A good introduction to these types of biochemical models is a paper by Novak and Tyson. One topology that can oscillate is three pools connected by arrows in a loop, as in Figure A. Here I have diagrammed a specific model that can be described by a set of differential equations. Differential equations define only changes in the system. We must know initial values, that is, values of the unknowns, at time equals 0. Some differential equations have well-known functions, such as polynomials, exponentials, or trigonometric functions as solutions, while others do not. However, it's always possible to generate numerical solutions using a computer. In order for the differential equations to have a solution over extended times, each pool must have at least two arrows, that is, relations, one that can increase the value and one that can decrease it. For example, rho, the circle, is inhibited by the cell wall with a value of z times zix, and is stimulated by itself with a value of x times xax. The inhibition of x by z is not direct. Rather, x is inhibited by the value of z TL seconds earlier. That is, the inhibition is delayed TL seconds. Thus, this is called a delay differential equation. These are the three differential equations that define the changes in x, y, and z each second. In the top line, x prime t is the change of x, which is found by multiplying the concentration of x by the concentration of z, TL seconds earlier, by the concentration of x, then by the parameter minus zix. To this term is added x times the parameters xax and xaxvm. Then dividing by x plus the parameter xaxkm. The other two equations are read in similar ways. These equations are actually code for the program Mathematica, which uses the double equal signs to represent the normal equal. One important feature of these three equations is that they are not linear. In the top equation, the first term has a product of x and z. In addition, the first and second equations have fractional terms, with x of t plus xaskm or x of t plus xaykm in the denominator. These terms implement the well-known Michaelis-Menten relation, but they also make the equations nonlinear. The force B term in the last equation represents an external force applied to the cell, which will be used in a later section. Since these three equations only specify changes with time, we need to know the initial values to start with. We expect these initial values to not influence the solution after much time, but they are needed anyway. Finally, we see the result of numerical integration of these three differential equations over 2,000 seconds. As you see, each of the three variables, x, y, and z, oscillate together with a period slightly longer than 60 seconds. As mentioned before, these numerical solutions were obtained using the application Mathematica. MATLAB is another application commonly used for projects like this. The four slider bars along the top of the figure enable us to easily change the values of the four most important parameters that define interactions between pools. The parameters xay, yaz, zix, xax. These are the values of the parameters for the preceding solution. A system like this typically oscillates only within certain ranges of the parameters, defining the interactions between the pools. How to find these values can be the hardest part of the problem. If we had three simple linear differential equations to solve, there are nice formulas to determine parameter values for oscillating solutions. If we had a linear solution with time lag, there are more difficult methods to find oscillations. We have both, so we have to search in a multidimensional space. This search would not be possible without the slider bars. Even with sliders, patience and persistence is required, but we found them. Here is the solution for the same system with a push, a sudden increase in the value of z, the cell-cell contact area, starting at 270 and lasting 20 seconds. After a lag of about half a cycle, the oscillations suddenly increase in size fivefold. It takes many cycles to decrease, and it's not clear from this graph that it will ever decay to the pre-push value. A longer simulation shows that values do eventually fall to pre-push levels, but the decay is not exponential. Now let's look at the solution for Z, the cell-cell contact area, as a phase portrait, a paradigm used previously in Chapter 1 of the series. The phase portrait plots the rate of change of Z on the vertical axis versus Z on the horizontal. A sine wave is a circle or ellipse in its phase portrait. Phase portraits are often used in the study of dynamic, that is, changing systems. A system moving along a closed curve in a phase portrait can be thought of as a planet moving around the sun in an orbit. The equation describing the system generates a force that holds the solution in orbit. The force can be seen as a basin of attraction with the solution rolling around in the basin. Here we see an actual basin in which I wash my face each morning. I have thrown in a marble, and if you look quickly, you will see it rolling around for a second before being trapped against the stopper. Now we will see the phase portrait of Z, the same solution seen earlier in the more usual plot of Z versus time, except here the push occurs at 430 seconds. The push will generate a sudden large loop, reflecting changes in the slope of the curve too subtle to see in the normal graph. Then the solution settles into large circles. These circles gradually get smaller, and eventually, after a much longer time than shown here, they merge with the early circles. Now we need to splash a little cold water on our face. This model is just a framework to hang things on. A real cell has many more pools and interactions. The circle, triangle, and rectangle are each complex. Many complexities may not be important for our observations, but we don't know which are and which are not. The circle in our model represents the row small GTPase, but humans have 5 families of small GTPases. The largest family, RAS, has more than 100 species. Each small GTPase requires 3 accessory proteins to function. The small GTPases can interact with each other to create their own oscillating system. The triangle in our model represents actomyosin rods that can push or pull by becoming longer or shorter by adding or subtracting subunits. But adding or subtracting subunits requires other proteins, such as formin. Humans have 14 different formins with different properties. Some have binding sites for GTPases, some do not. You may think, but a tunicate is much more simple than a human. The tunicate is more simple than a human. We diverged from a common ancestor about 400 million years ago. But a tunicate is a chordate and is known, for example, to have analogs to most of the human small GTPases. Building a model does have important value. It provides discipline. If you can't build a model, you don't really understand the problem, or at least the entire problem. A model can suggest experiments and help analyze results. If a result isn't consistent with the model, change the model. That's the point, isn't it? Systems with components that change with time are found in all fields of science, medicine, and engineering. Describing these systems with differential equations, finding solutions, and developing graphical methods to understand them is such a valuable skill that the study of nonlinear dynamical systems forms the subject of courses taught in most universities. Epithelial cells that contract and expand rhythmically are found in many tissues and play important roles in embryonic development and adult life. Understanding these processes may start with the individual cell, but understanding the interaction between cells ultimately defines the behavior of tissues. In earlier chapters, we have seen an example of almost complete synchrony of contraction among the cells of each member of a detached pair of ampulla, and a traveling wave in the cells of a detached single ampulla. A model for the detached single ampulla will be the subject of the next chapter. A traveling wave will be shown to be the only possible configuration of periodically contracting cells in a cylinder of constant volume. Stay tuned.